Hello, my name is Michael Speth. I'm a director of systems engineering at SiPearl in Duisburg. I want to talk to you about SiPearl, its mission, markets, and the role of RISC-V in our current and future products. SiPearl is a member of the European Processor Initiative, or short EPI. It was founded as a new European processor company to turn the IPs developed by the EPI into real silicon and to commercialize them. The EPI has been kicked off in 2018 as a consortium of 27 major companies with the agenda to develop a sovereign high-performance processor for HPC. The initial target is to enable the European supercomputer programs. However, this will only be the first product of a processor family targeting all relevant HPC segments. Since sovereignty is one of the major objectives of the API, RISC-V naturally plays an important role for us. Just some more background on SiPearl. We were founded in 2019 by our CEO Philippe Norton and received seed money via the Horizon 2020 program. Our headquarters is in Maison Lafitte near Paris, and we have a second equally sized design center here in Duisburg. The first employee joined in January 2020, and since then we have grown to a small but fully featured semiconductor company. Currently, we have 22 experienced employees, mainly originating from ST, Intel, Atos, and Marvell. Together, we look back at having designed and delivered hundreds of million chips. We have all required SPs on board. We have the design flow and the IT infrastructure up and running, and we are well into the design of our first product. Based on our ongoing Series A funding, our team will grow substantially, also here in Duisburg. SiPearl was founded to generate a European high-performance computer ecosystem. Our first target market is high-performance computing, delivering processors for exascale systems. We have chosen ARM's new processor family Neoverse for its outstanding performance of the cores and the SoC peripherals, but more importantly, for the ARM server processor ecosystem. By having full control over the IP and using open architectures like RISC-V, we can guarantee security, safety, and data protection for all of our products. Next to enabling exascale computing, EU sovereignty is the major charter of SiPearl. We will grow a European ecosystem and value chain, ensuring that European-funded projects can benefit from our products to generate new European technologies. As high-performance computing gets important in all technology fields, thus we ensure the competitiveness of European key industries. The flexible common platform is the main vehicle for this. SiPearl will work together with European partners in a platform approach to embed acceleration in our general-purpose processors and thus enable disruptive new products. In summary, our value proposition is P3S: performance, security, safety, sovereignty. The markets that we want to address follow the agenda of the EPI to enable European sovereignty. But certainly we also target to market these solutions worldwide. Backed by the expertise of our EPI partners, we will initially focus on the market for European supercomputers, enabling the first exascale systems. Next, we will address the technically adjacent market of cloud computing, which is growing at a huge pace and where initiatives like Gaia-X push for European sovereignty. As we further grow, we will also address specialized segments like edge computing and infrastructure, and finally also markets in the automotive and industrial area, which are so important for Europe. Now, a valid question is, how do we get all this done with such a small team? This is only possible due to our strong partnerships. On the one side, there is ARM. With ARM IP, we have licensed the most widely used ISA on the planet. ARM IP provides an outstanding performance while having significant advantages in terms of power consumption. But more importantly, ARM provides incredible support for design and modeling, as well as elaborate tool chains and libraries that are growing across all the segments that are relevant for us. This provides a huge productivity for the team. On the other side, there is the EPI. To start with, all the EPI partners bring in their system expertise to define the chips, but they also actively engage in design and verification, as well as the integration and bring up in the final products. In today's software-driven world, the software ecosystem is a major key factor for successful products, and the ARM ecosystem is really outstanding. Starting from the OS, where multiple alternative distributions are available, middleware solutions that support virtualization and container packages, a big community of user groups and consortiums porting and optimizing applications. So with ARM, we have both full control of the hardware IP that we integrate in our systems and the possibility to benefit from this huge ecosystem. So enough of the ecosystem. How does an HPC processor actually look? Generally, an HPC processor is a general purpose processor, or GPP, optimized for the HPC use case. The key ingredient of a GPP is the core cluster, providing the processing power. In addition, the amount of on-chip cache memory is essential. In HPC systems, you will typically see 3 cache hierarchies, 2 that are individual to each core, and 1 last-level cache hierarchy common to all cores. To feed all this processing power with data is just as important as the processing power itself, so an ultra-high-speed interconnect linking all these cores is essential. You need interfaces to attach as many and fast memories as possible, and high-performance interfaces to link the chip with other chips in a multi-socket setup and to attach accelerators like GPUs. Finally, to coordinate all this horsepower, you need considerable resources for system and power control, security hardware to protect the system and its data, and typically you also add some magic spice in terms of hardware accelerators to optimize for certain workloads. Supercomputing is extremely demanding in terms of memory requirements, both in size and bandwidth. External interfaces are also a challenge, since you need to integrate huge clusters of chips to one joint system, and the use of accelerators only makes sense if their interface is not a bottleneck. If you base a supercomputer on standard GPPs, the resulting system is always a compromise. This is why for our first product, RIA, we focus on optimizing these important parameters for supercomputing. Initially, it looks quite similar to a GPP solution. However, the GPP components are now part of a chiplet. Using this approach, we can integrate it with chiplets from other vendors in other technology on a common interposer. This allows us to attach ultra-fast HBM memory, which achieves speeds almost matching integrated memories. For workloads focusing on data processing, this will yield a huge boost in performance. In addition, we add a dedicated die-to-die interface, allowing to integrate accelerators almost as if they were part of the chip. Based on this architecture, using the latest memory and interface technologies with an optimized mesh topology and with the right blend of memories and interfaces, we project to outperform systems based on GPPs considerably. This approach is complemented by the extensive use of RISC-V technology. Due to its open architecture, RISC-V is a natural choice for sovereign systems. We use RISC-V-based processor clusters for the security-relevant parts of the design, but also for performance-critical system and power control functions. In addition, most of the hardware accelerators that we will integrate are based on a RISC-V approach. The resulting system although initially optimized for HPC, also provides an excellent baseline to scale it to other markets. Let's revisit our target markets. As we move from HPC markets towards cloud, edge, and automotive, some priorities change. Security requirements increase significantly. Whereas HPC operates in isolated environments, in other markets, systems are much more exposed to attacks via the internet or even physically. Generally, you also observe an increasing specialization of workloads for these markets, for example, towards AI and machine learning. At the same time, these markets are much more price and power sensitive. The right way to meet these requirements is by the use of more and more specialized accelerators. However, developing these accelerators requires deep knowledge of the target applications. This expert knowledge resides in the many mid-sized companies which are hidden champions in their fields, but also in innovative startups. To address this, the EPI follows its common platform approach. The common platform provides a framework comprising both hardware and software for integrating customized functions in a chip. It will allow for many different setups, traditionally over PCIe on adapter cards, or in the package via fast inter-chiplet links or even on the interposer, using loose coupling or coherent interfaces via CCIX or CXL. This not only allows the GPP to use the accelerator as if it were part of the design, but also the other way around, the accelerator can use the extensive memory and interface resources on the GPP to allow for completely new applications. With this approach, we enable an innovation ecosystem in the European semiconductor landscape, and given the nature of such accelerators, I'm sure the RISC-V architecture will play a major role in this. I'm happy to join this working group in order to get a better idea what is needed to make the common platform an ideal partner for RISC-V, so that we will see a lot of RISC-V-based common platform solutions in the near future. This concludes my talk. I hope to have interesting follow-up discussions with some of you, and I also explicitly want to mention that we are hiring. So if you know someone who might want to join us in this ambitious project, please spread the word.